Hello friends. So, in first lecture we understand what is the difference between solid and fluid. Next we'll understand the fluid properties. So this is very important. So first we will understand the property, that is density or mass density or specific mass. So density is also known as mass density or specific mass. So we basically know that mass per unit volume is known as density, but mass per unit volume at specified temperature and pressure is known as density of the fluid. So this is the actual definition of the fluid, actual definition of the density. So liquids show negligible changes in density with temperature and pressure, but gases show change of density with temperature and pressure by ideal gas equation. So what is the ideal gas equation? That is the PV equal to mRT. So liquid are incompressible with respect to gases. Okay, so liquid are incompressible with respect to gases. So this is very important. Okay, so now what is the definition, what is the formula of density? That is rho, that is equal to m by v. So what is the unit of m? That is kg. And what is the unit of volume? That is meter cube. So this is the SI unit. Okay, now here rho is the function of pressure and temperature. Okay, so here rho is the function of pressure and temperature. So for gases there is ideal gas equation, and for liquid consider there is water, and at 1 atmospheric pressure and 4 degrees Celsius temperature, density of water, that is we know that is maximum, that is 1000 kg per meter cube. And the same atmospheric pressure, 1 atmospheric pressure and 20 degrees Celsius. So here there is 4 degree in first case, and in second case that is 20 degrees Celsius. So density of water, that is 998 kg per meter cube. Okay, and if the pressure is highly increased, that is 1000 atmospheric pressure and 20 degrees Celsius temperature, the density of water, that is 1003 kg per meter cube. So not too much increased, little increasing increment is there. So here the delta P difference, pressure difference, that is 1000 minus 1 atmospheric pressure, that is 999 atmospheric pressure. And what is the density change? The lowest density, that is 998, and the highest density, that is 1003. So what is the density difference? That is 5 kg per meter cube. So if you want to calculate del rho by rho percentage, that is equal to 5 by 998. So rho is the initial density, lowest density. So 5 by 998 into 100. So that is approximately 0.5%. So for water, del rho by rho percentage, that is approx equal to 0.5%, and for any fluid, if it is less than 5%, that is known as incompressible fluid. Okay, so for water it is less than 5%, so that is why water is known as incompressible fluid. Density does not change. Density changes are there, but there is a little changes are there. So that is why we can neglect these changes. So that is why it is known as incompressible fluid. Although all fluid are compressible, but a fluid is said to be incompressible if its percentage density changes is less than 5% for any pressure change. So this is very important. This is less than 5% for any pressure change. Okay. So this is all about the density. Now we will focus the next property, that is specific weight or weight density. So specific weight, that means, so it is defined by the ratio of weight of the fluid to the volume. So weight omega, this is denoted as omega, that is specific weight or weight density. Omega, that is equal to weight per unit volume. So what is the unit of weight? That is Newton, and what is the unit of volume? That is meter cube. So Newton per meter cube is the SI unit. So it is a gravitational force on volumetric mass. So it is the another definition. Okay, so it is a gravitational force on volumetric mass. So if you want to calculate omega, that is equal to weight per unit volume, we know that, and weight, that is equal to mg by v. So that is equal to m by v, we know that rho. m by v is rho into g. So omega that is equal to rho g. Okay, for water, omega that is equal to rho of water into g. Rho of water that is 1000 kg per meter cube, and density g is the gravitational acceleration. So g that is equal to 9.81 meter per second square. So if you calculate that is 9810 Newton per meter cube. Okay, 9810 Newton per meter cube. Okay, so if you want to calculate specific weight for water in kgf per meter cube, that is will be 1000 kgf per meter cube, and 1 kgf that is equal to 9.81 Newton. Okay, so kgf is the force unit. Okay, this kgf that is the force unit. Now relative density. Relative density means RD, that is the relative density, that is density of 1 by density of 2. Density, it is the ratio of density 1 by density 2. Okay, so this is the relative density. Specific weight is the ratio of the density of the fluid to the density of standard fluid, or you can say that it is the specific weight of the fluid to the specific weight of the standard fluid. Omega is the specific weight. Okay, specific weight of the fluid by specific weight of the standard fluid. Okay, so for liquid or gas, for liquid or solid, that is specific gravity that is equal to density of fluid or divided by density of water. So this is very, very important. So there is a density of fluid, any fluid, but here the standard fluid, that is water for this case, and density of water, that is 1000 kg per meter cube. Okay, and gases, for gases, the specific gravity SF that is equal to rho f by rho of air, and rho of air, density of air that is equal to 1.23. So remember this data, that is density of air that is equal to 1.23 kg per meter cube, and here density of Hg that is equal to 13.6 into density of water. Density of gasoline that is equal to 0.75 density of water, and density of wood that is equal to 0.6 density of water. So remember this data. Now the last property, that is the bulk modulus and compressibility. So what is bulk modulus? It is the property of the fluid which defines the opposition under compression. So this is very, very important. This is the property of the fluid which defines the opposition under compression. So it is analogous to modulus of elasticity under compression in solid. Large value of bulk modulus defines more opposition, that is less compression. So less compression, so less compressibility. So compressibility is inverse of bulk modulus. Liquid has large value of bulk modulus, so K of water that is equal to 2 into 10 to the power 6 kilonewton per meter square. Okay, then gases have bulk modulus that is 100 kilonewton per meter square. So liquid are incompressible with respect to gases. Okay, so now we will see that. So this is the piston cylinder arrangement, and here the initial volume. So this is the piston cylinder arrangement. So this is the piston cylinder arrangement here, and this is the initial volume. Vi is the initial volume, and Pi is the initial pressure. This is the initial position of the piston. Okay, now if you increase the pressure P plus dP, then the piston going down, and the volume V final that is equal to V minus dV. dV means the change in volume. So dV must be this volume which is changes. So the final volume is decreases due to increase in pressure. Okay, now if you want to calculate the volumetric strain, we know that volumetric strain, that is delta V by V. Okay, delta V is the change in volume divided by original volume. So that is equal to V final minus V initial, V final minus V initial So V final minus V initial, that is equal to V minus dV, okay, V minus dV by minus V by V, okay. So this is the final volume minus V, this is the initial volume by V, so that is equal to minus of dV by V, okay. So from here dP, we know that dP proportional to epsilon V, okay. So dP, that is equal to, there is a proportionality constant K is the bulk modulus, and into epsilon V. So from here K equal to dP by epsilon V. So K, that is equal to dP divided by epsilon V from this, so minus dV by V, so minus dV by V, so that is equal to dP by d rho by rho. This is applicable for liquid or gas. So why this is minus dV by V, that is equal to d rho by rho? So we know that rho, that is equal to m by V. If m equal to constant, rho V, that is equal to m, that is equal to constant. So from here you can say that ln rho plus ln V, that is equal to ln m. So d rho by rho plus dV by V, that is equal to 0. So that from here minus dV by V, that is equal to d rho by rho. So from here minus dV by V, that is equal to d rho by rho. So this is the formula for bulk modulus, okay. So for incompressible, if there is incompressible fluid, compressibility 0. Why? If dP is greater than 0, then K tends to infinity. So dP is greater than 0, okay. If dP is greater than 0, so K, we know that dP K equal to dP by epsilon V, okay. So for incompressible fluid, compressibility, that is equal to 0. So incompressible fluid means compressibility K, this bulk modulus tends to infinite, and if the bulk modulus is infinite, so beta, that is equal to 0, because beta equal to 1 by K, we know that, okay. So compressibility beta, that is equal to 1 by K. So beta, that is equal to 1 by K. What is the K? That is dP by epsilon V. So here, so K equal to dP by epsilon V. So from here, that is equal to epsilon V by dP. So that is equal to epsilon V, we know that minus dV by V by d rho. So that is equal to d rho by rho by dP. So from here 1 by rho d rho by dP. So beta, that is equal to 1 by rho d rho by dP. So this is very, very important. So for that case, so K equal to rho dP by d rho, and here beta equal to 1 by rho d rho by dP. So this is the case here, and here if you draw the PV diagram, so this is the initial position, this is the initial pressure, this point, this is the initial pressure. So here this is the initial pressure, and there is the initial volume Vi, okay, when the piston is in this position, okay. Now when the pressure is increases, so here the pressure, this is the final pressure P plus dP, and this is the final volume minus dV, okay. So final volume V minus dV, okay. So if you want to calculate the slope, that is equal to dP by minus dP. So because this is minus dP, the volume is decreases. So we know that K equal to dP by minus dV by V. So K equal to V initial, this V is the initial volume, into dP by minus dP. So K proportional to minus dP by dV. So K proportional to slope of PV diagram. So this is very, very important. So slope of it, so dP by dV, that is the slope of PV diagram, okay. So in that case, so here PV diagram, so theta is increases, so theta 3 is greater than theta 2 greater than theta 1. So if P increases, then theta increases. Why? If P increases, here if the P is increases, then theta will increase, and if the theta is increases, then K increases, because K proportional to slope of PV diagram, okay. So K increases, and if the K is increases, then beta will be decreases, okay. So beta is inversely proportional to the bulk modulus, okay. So as pressure increases, the opposition for the further compression increases. So bulk modulus increases. Bulk modulus is not constant property. Ability of compression under pressure is known as compressibility. If there is no change of density with pressure, then the fluid is said to be incompressible, okay. And there is another there is one question. Try to do this question by your own. So this is my handwritten notes. You can download it from the description. If you have any query, you can ask me. Okay, thank you.